we're now ready to actually do software testing with ACL2s. So let's see what that looks like. Okay. Now I'm going to go ahead and create a new project. So this is everything from scratch. So new project is just a project, and let's call it test. Actually, let's call it sum up to n, because that's the only function we're going to define. Okay. So that's the name of the project. Inside of that, I need to have a list file. So let's create that. It's an ACL2 list file inside this project. And again, I'll just call it sum up to n. Okay. Now, you're also going to need another file that actually has the testing harness. ACL2s does come with a testing harness, but it's a little rough, so I try to put kind of a wrapper inside it. Okay. So let's build another file that will have that. And this file we're going to call testingharness.lisp. And again, it's just a regular ACL2 file. Okay. All right. So here it is. And this is input that I'm actually giving you. Okay. This is part of the assignment. I just give you this input. So all you need to do is cut and paste it into your file, testingharness.lisp, save it. Okay. And then go to the ACL2s menu and select certify as book. It's okay. Right? It's going to give me an error because I didn't actually run it first. So it says, I'm not sure it's actually going to work, but I know it's going to work because I've done it already. So, you know, you can be sure of that. So just hit, yeah, sure, go ahead and build it. Okay, it's finished. Okay, so now we can go to our list file. Okay, and we can actually write the code. Okay, so a couple of things that I want you to do. The first thing is just always start with this line in package ACL2. Written like that. Okay, and all that does is it says, look, all the functions that I need are actually in the ACL2 package, and a package is actually like a Java package. Okay, so you know, we just want to make sure we're all in the same place. The next thing that I want you to do is to say include book and then double quote testing harness. Okay, and what that does is it actually brings the testing harness. So let's make sure that we're okay so far. So yeah, we've included both of those. Everything looks like it's working just fine. Okay, so let's define the function. And we did this before, but I'll just define it again. Define sum up to n of n. If n is a positive number, then what we want is sum up to n of n minus 1, and we'll add n to that. Otherwise, the answer is 0. Okay, so there's our function, and I'll just click this. Yes, that has submitted. Now the key moment. Let's actually write some tests. Okay, so the first test that we have is something called check expect. Okay, this is the way we do unit tests. And remember the way that unit tests look like. Unit test says, I know the answer to this particular question. So this obvious one to start with is sum up to n of 0 should be equal to 0. Okay, we should do another one. Sum up to n of 4 should be equal to 10. That's just one that I know. Okay, we can do some others, like for example, the sum up to n of 5. Of course, that's 15, but I'm going to write it like this. That's 5 plus the sum up to n of 4, right? So maybe I don't know the correct answer, but I know an expression that will do the correct answer. Okay, so I can actually test that. All right. Well, let's see how we're doing. These are our unit tests. Okay. All the unit tests passed. Okay. Let's look over at the testing harness. I'm sorry. I forgot to start up ACL2. Okay, so when we go here, we see that in fact all of them succeeded, right? You know, check expect is, you know, all of those are good. Just so that you can see it, let's try something that's false. Okay, let's do check expect sum up to n of 2 to be 12. Okay, that shouldn't work, right? Okay, notice that it actually rejected it. When it went up, it said, no, I don't believe that. And here it's telling us, I'm sorry, I was unable to test that, right? So that's good. That means our test cases probably have a chance of working, right? You know. Okay, so let's let's now look at more complicated things. In particular, I want to look at some little theories. Okay, so how do little theories work? Well, they're supposed to be kind of mathematical statements, right? That are valid. So let's this is my first little theory, and I'll do it with check little theory, right? And now I will simply write the little theory. Okay, so my little theory is that sum up to n of n should always be greater than 0. Okay, or at least greater than or equal to 0. So let's do that. This should be greater than or equal to 0. Okay, so I'll hit next. And yeah, it succeeded. Now let's look at the output, okay? And this here is something important for you to see, okay? So it says I tried 500 examples, okay? 416 of those were unique, so you know, a little bit of random play. And I tried it for n equal to 0, and it worked. I tried it for n equal to a list containing the letter C. That's actually what that says, and it worked. I tried it when n was the pair of a 0 and a 0. You notice that it's actually trying for just crazy things of n, right? I only intend for this to be true when n is an integer, right? So let's fix that. Okay, so let's undo this. And this is the reason that we actually want to have things like this. Implies integer p n, okay? And this theorem now is only true when n is an integer. Now look at what's going to happen this time. Again, it's true, right? But now right here, look at what he tested it with. I tried it when n is equal to 3. I tried it when n is equal to minus 3. I tried it when n is equal to minus 4. It worked in all those cases. Okay. Again, you might actually say, wait a minute. That's not really what we meant, right? So you'd be right again. Okay. What we meant is this only holds when n is an integer that's greater than or equal to 0, right? So let's add that. And n is an integer and greater than or equal to n0. Let's try again. Okay, so now let's look at this. Now we see that I tried it with n equal to 7, n equal to 9, n equal to 451. That's much better. You see, we're only trying it with 500 different cases, right? So we want those 500 to actually be the kind of cases that we expect, right? There's no point in testing it with n equals Fred, right? Because we're never going to call sum up to n with Fred, okay? We're going to call sum up to n with a positive number, or at least a non-negative number. So let's check it with that, okay? So that's one reason that little theories often have those kind of conditions, okay? Let's try another little theory. My theory is going to be that if n is an integer and n is greater than or equal to 0, that sum up to n, and I'm going to say that is equal to something, okay? And I'll say that that is actually equal to 10. Again, this is false, right? But I just want you to see what happens. Oh, that didn't work, okay? Now let's look at the output, okay? And here's what it says. We actually tried it, okay? And we tried it, and we tried it with 972, and it didn't work. We tried it with 645, and it didn't work. We tried it with n equal to 6, and it didn't work. So the conjecture is just false, right? Here are 3 counterexamples, okay? The nice thing is that it actually gives you some concrete counterexamples, so you might use those for debugging. It's like, oh, wait a minute. What happens when n is equal to, oh, I would pick 6, right? That's the smallest one. And you'll see that, in fact, it can't be true. Notice this, though. It also says, oh, here are some cases in which your conjecture was true. You see, I tried it with 4, and it actually worked, right? That's kind of nice, isn't it? Okay. So what's happening there is that it's true some of the time, it's false some of the time. But again, by specifying the types that we're interested in, only positive or non-negative integers, right? Then it only tested it for those. And that's great because we can look at it and see, oh yeah, this is actually useful feedback. You know, I would hate it for it to tell me, oh, and it didn't work when n was equal to the string Fred. It's like, well, I wasn't expecting it to work for that, right? So always put in those things. Okay, so this is actually false, so I'm just going to get rid of it, okay? I could have lots of other little theories, by the way. I could have, for example, that if, well, actually, I just put one in here. Check this little theory. Let's say that I have 2 integer n, which is greater than or equal to 0, and integer pm, which is also greater than or equal to 0. Okay, and by the way, it is the case that m is greater than n. Okay, then this should mean that the sum up to m of m is greater than the sum up to n of, oops, this should be n, of n, right? All right, that's a little theory. Let's see if it's true. Yeah, it looks like it works. And you see it tried it with m is 74, n is 2, m is 10, n is 4, and so on. So this is actually a very powerful technique for testing. Okay. Now, finally, let's say that you do a lot of these things, and what you discover is that your theories appear to be true. Okay, so it is time to go one more step and actually prove that those things are true. And the way you do that is with something called define a theorem. Okay, and my theorem is going to be sum up to n non-negative. I actually find that I've run out of names after a while. And here is what I want my theorem to be. It's actually the same as this little theory. Okay, so let me go with that. Okay, and let's see if you can prove it. Oh, well, will you look at that? Okay, so it actually went ahead and it did a whole proof, and it came up. It actually doesn't show us the proof unless it really needs to, and it says, yeah, good job, you actually have a true theorem. Okay, I'm going to undo that theorem, because one of the observations I want you to see is that the way that we defined n, this actually is true always, not just when n is a non-negative integer, right? So this is in fact a different theorem. I'm going to tell you that it's a more useful theorem to prove, and the reason for that is that, well, it's true for all n, right? Not just for some of m, like when n is a non-negative integer. So if we can actually prove this theorem, that's going to be more useful, is more widely applicable. And let's see, yes, that one is also true. Okay, like I said, that's not a surprise because of the way that we define the function. Okay, if you give it something that's not an integer, it just immediately returns 0. Okay, now I do this for the final theorems, right? I don't do this for the little theories, because in the little theories, since we're actually randomly testing, I want to give the theorem prover a hint as to what kind of things I wanted to randomly test with, right? You know, sum up to n is about integers. Don't even try with 3.5, for example. Okay, so that's a theorem that's true. Okay, all right. Now here's another theorem that I might try. And in fact, I'm going to do it as a little theory first. I like doing it as little theories first because of the testing. I can actually see if it's not true. And what I'll say is that it is equal sum up to n of n. You might know this from your college algebra class or high school algebra class. That's actually equal to n times n plus 1 over 2, right? So it's equal to n times n plus 1, and then take that divided by 2. Let's see what happens. It proved it, right? Well, actually, I shouldn't be too impressed. What it did was it tested it with 12 and 4 and 0 and with 1,000 other numbers. 807 was unique, and it held, right? Well, I happen to know that this is true, so I really shouldn't have been that impressed. However, let me try to prove it. Let's see what happens. This is a direct formula for that, and what I'll say is that equals sum up to n of n, and I'll just get this little expression. Okay, let's try. Oh, that's not a good sign, right? It went green and immediately went white. That means it didn't work. Let's look at the errors, right? And it says, hey, I believe that it works, and I tested it in this case. When n was 15,348, good job. When n was minus 1, it worked. When n was equal to 0, it worked. But unfortunately, when n was a complex number, 1/12 minus 2 over 11i, oh, dear me. Okay, so it doesn't seem to work in some cases, but at least all of the counterexamples that I found seem to be just weird numbers. Okay, so let me fix that, because I don't need this theorem for everything. I only need it when n is an integer. And actually, I'm happy if it's just when n is greater or equal to 0. Let's see. I wonder if he's going to be able to prove this. Look at that. Okay, so that's what a theorem prover does. By the way, here's the proof. It actually used recursion, right? You see, it tried this, it tried that, it tried that. It actually did a lot of work to be able to give this to us. Okay, and it also tested it to make sure as he went through. So it said, yeah, this appears valid. So that's how we prove theorems in ACL2. Okay. So what I'm going to ask you to do in the assignment is I'll ask you to write some code like this function right here. Okay. Give me some unit tests. The unit tests are always using check expect. Okay. Give me some little theories, and we check those with check little theory. And the little theories are properties that you think are true, okay? And don't forget to add lots of statements in the implication. So you can say, I expect this to be true, but my inputs really should only be integers, or they should only be integers between 1 and 10, or whatever is applicable, okay? And then finally, try to prove a theorem that actually says this code really, really, really works, okay? And sometimes ACL2 will actually prove it. When it does, it surprises me, okay, because I'm used to it failing most of the time and needing help, okay. I'm not going to ask you to actually drive the help, okay. What I'm going to ask you is simply to try, okay. Try to see if ACL2 proves it. If it does, fantastic, way to go. If it doesn't, you know what, ACL2 has limitations. But I want you to see the whole span from unit testing to theorem proving.